Hello. I hope I'm audible and the slide is visible to all of you.
Yes, ma'am.
Yes, ma'am.
Hello. Am I audible?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Okay, fine. So today we'll start with the next unit, that is your nuclear magnetic resonance spectroscopy. Till now, up to our 11th unit, we have completed many molecular spectroscopic techniques as well as some atomic spectroscopic techniques. Okay, so we'll not go just with a glimpse of idea. I'll just refine the things that in molecular spectroscopy you had noticed that there is interaction of your uh, interaction of your radiation with the matter. However, what was happening there? There, near the molecules, you are having different surrounding effects too. However, while studying the atomic absorption spectroscopy or atomic spectroscopies, that time you observe that we are just vaporizing, we are just making the atomization process fast, then we are just going for the atomic absorption or emission studies. So that part is over for us, that atomic spectroscopy and emission spectroscopies and molecular spectroscopies, Raman, IR, everything we have covered. So till now, you might have a clear-cut idea that these spectroscopies are how helpful these are. Okay, again and again, I was telling you that through this program, you will be like clear how to analyze a sample, how to analyze soil samples, and how to use these analytical methods to study various contaminations that are present in your water or any kind of sample. Okay, let me put this NMR spectroscopy in this way that it is useful, but how it will be useful for you people, like chemist. As a chemist, I was telling you in the last class that as a chemist's role is everywhere. If you go to R&D sectors of industries, if you go to chemist forensic departments, wherever you go, you'll be using these analytical methods. And up to last class, I was showing you all your materials that has been uploaded in the IGNO website. I was telling you it is sufficient itself for the spectroscopic methods. Everything is there. However, this NMR spectroscopy is bit you need to understand it very carefully. That if you remember my first class when I was telling you about the electromagnetic radiation and electromagnetic spectrum we discussed from gamma ray to radio frequency region radiation. So I told you that time that when a radiation is falling on matter, some change happens with that matter. Why? Because it is getting bombarded with a radiation of high energy, right? So that change in matter may be your rotation, maybe your vibration, maybe ionization. In that way, various spectroscopic tools are there to study this kind of matters. Okay, so now while dealing with the NMR magnetic resonance spectroscopy, uh, it's about all about the interaction of radio frequency region radiation with that of matter. Okay, so what is happening here? In my past class, I was telling you two category of spectroscopies: molecular spectroscopy and resonance spectroscopy. And under resonance spectroscopy, your NMR, EPR, all these will come under resonance spectroscopy. Okay, so let's move without because today we have to finish NMR spectroscopy, mass, as well as we have to deal with some structural elucidation. Like suppose you are in a pharmaceutical industry and you are synthesizing some pharmacomolecule, but whether your hand is perfect to prepare that molecule or not, how do you know? You go for certain characterizations by using NMR, IR, microwave, UV visible, whatever we have already studied. By using these spectroscopic tools, you can find out whether the molecule you have synthesized is good or not, if it is pure or not, if it is suitable for marketing, suitable for the uh, uh, what to say, that methodology you are following, that is also suitable or not. Everything you can characterize through this kind of spectroscopies. So coming to this nuclear magnetic resonance spectroscopy, most commonly it is known as your NMR or MRS, magnetic resonance spectroscopy. Okay, here you will be dealing with local magnetic fields around the atomic nuclei. This is coming under your resonance spectroscopy, I was telling you. So the sample is placed in a magnetic field and the NMR signal is produced by excitation of the nuclei sample with the radio waves. If you remember all the spectroscopies till now we have studied, there was interaction of the radiation from the source was there, then sample compartment was there, then monochromator was there, then detector and your output device. And in many spectroscopies, we have also observed that before the sample we kept monochromator, and in some we kept after the sample compartment. Why so? I have also discussed that. So this in here, what is happening? That matter you are going to interact that matter with the radio wave radiation. Okay. So what will happen? The intramolecular magnetic field around an atom in a molecule changes the resonance frequency. So the intramolecular magnetic field around that atom in a molecule changes the resonance frequency. See, when the excitation will happen, when the molecular coherence, molecular frequency change, as well as the frequency of radiation, whatever it is observing, that coherence will happen. Then only that resonance will take place and it will go to the excited state. In detail, slowly we'll be seeing the instrumentation and all other things. Okay. So, as the fields are very unique and highly characteristic to individual compounds, in modern organic chemistry practice, NMR is a definitive method to identify the organic compounds. How to do that also we'll be discussing in today's class. How to analyze these organic compounds by using the NMR spectroscopy. Before that, you have to understand the fundamentals of it, how which kind of atoms will give you, which kind of molecules will give you your NMR, can be studied through NMR. That is also a point. So many nuclei may be studied by NMR techniques, but hydrogen and carbon are the most commonly available. Okay, why so also subsequently we'll see. Whereas IR spectroscopy reveals the type of functional groups present in a molecule. While discussing IR spectroscopy, we have already discussed these portions. And functional groups, they will give signal in various IR regions, and depending on that frequency, you can predict which functional group is present in your molecule. Subsequently, we'll just do structural elucidation. Don't worry about that. We'll just first try to understand these concepts. So, NMR gives information about the number of magnetically distinct atoms of the type being studied. Okay. When hydrogen nuclei That is what is protons are studied. For instance, one can determine the number of each of the distinct type of hydrogen nuclei as well as obtain information regarding the nature of the immediate environment of each type. Okay. Each and spectroscopic tools, you are not studying the molecule as such. Some certain environment around it will be there. That environmental effect is also there with spectroscopies. The day I was showing you the fluorescence spectrophotometer, which is present in my lab, I was telling you that when you are putting different solvents in cuvette, if you are changing the polarity of the solvent, your spectrum of that particular molecule is also shifting. Why so? Because it is the environment is affecting in a great way. Okay, that molecular environment is affecting in a great way, but indirectly from the spectral analysis you can predict it is in which kind of environment. It is in the polar environment, non-polar environment. All these things you can predict. If you are attaching a conjugated molecule to the your normal molecule A, and then you will find a shift in the spectrum. From there you can also predict, okay, whatever attachment I had done during my synthesis part, it's showing through spectrum also. Okay, then further characterization you can do through various techniques. Okay, so similar information can be determined from the carbon nuclei also, and the combination of IR and NMR is very good. Combination of your IR and NMR for the spectral and structural elucidation is very very important. In the last unit, in today's class, in the last unit, we will do by taking one two examples how to elucidate the structure, which is your last unit. Okay, so UV visible spectrophotometer, by using that, we can get information about the functional groups of the organic molecules. Okay, whether conjugation is there, whether not, and functional groups you can predict which is there, or keto group is there. Every information you can get. We have already discussed while discussing UV visible and IR spectroscopic tools. And elemental analysis, you can get information of CHON and S percentage from there. Then NMR spectrometry, depending on the magnetic character of the atomic nucleus, it gives information about the skeleton of the molecule. Okay. So other spectroscopic methods are related to electrons. NMR spectroscopy is related to nuclei. This is a point you should understand, and this is the difference with the NMR spectroscopy. And for NMR, it requires very long wavelength radiation, such as your radio wave. I was telling you, we are telling that okay, spectroscopy is all about interaction of radiation with matter. As a whole, we are telling this statement, okay? But that radiation can be radio wave, it can be microwave, it can be IR region radiation, it can be UV visible radiation. So that is why different segments or subsections of the spectroscopies are coming into picture. So this spectroscopic method is really extremely vast subject, and through this program you are at least knowing about all the spectroscopic tools, but it is a very lengthy topic because 14 units with each unit covering a single spectroscopy is very tedious. But apart from that, I think towards the end of the spectroscopic methods you will be very clear about all the spectroscopic techniques. So, for NMR, it requires a very long wavelength regeneration, that is radio wave, and as there is no need for breaking of the molecule, here breaking, making of the molecules is not happening. The samples can be reused in NMR. That is the best part. The sample can be reused because, as I was telling you in my last class, cost effective way is also we have to see which method is a cost effective way. That is also a point because as such your instruments are so costly, and if you are going for a cost effective way, that is very important. Here the sample you will be preparing so much by putting so much effort that you can reuse in the NMR. The disadvantage is relatively large amount of like milligram amount of your purified substance is required. If you remember the UV visible fluorescence spectroscopy part, there we used micromolar concentration. Micromolar concentration. It was quite enough for the study purpose. Let me tell you why. If you understand, then the energy gap between your ground state and the excited state is quite high there. If it is quite high, and here the energy gap between E1 and E2, that is your ground state and excited state is low, then what will happen? If you remember about the Boltzmann distribution population we have studied, population is important. If your energy gap is more, then most of the molecules will be available in the ground state. But here for the NMR, since the energy gap between ground state and excited state is less, then due to thermal activation also, some of the molecules out of that 100 or 200 molecules, some will be in the excited state. So to get a better quality, better sensitivity, better intense peak, you need more amount of the substance too. Okay, so here you need more amount of large amount of the compound. That is the disadvantage with this NMR spectroscopy. So preferably the sample should be dissolved in a solvent because NMR analysis of solids required dedicated magic angle spinning machine and may not give equally well resolved spectra. Okay. So, this NMR spectroscopy is based on the fact that some atomic nuclei acts like a small magnet and rotate around their axes. If you see this figure 1, that is the magnetic field associated with a spinning proton. The nuclei, while spinning, it creates its own magnetic environment also. And the spinning proton resembles like a tiny magnet. Okay, it creates a magnetic field around itself, around itself. Okay, so the magnetic properties of nuclei come to this slide. So all nuclei carry a charge that you must know. So, in some nuclei, this charge spins on the nuclear axis, and this circulation of nuclear charge generates a magnetic dipole along the axis. Okay. The angular momentum of the spinning charge can be described in terms of its quantum spin number I. You must understand this quantum spin number, and these numbers have values 0, half, 1, 3 by 2, like that. So depending on the spin numbers, you can predict whether that will be sensitive for the studying through NMR spectroscopy or not. So intrinsic magnitude of the generated dipole is expressed in terms of the nuclear magnetic moment mu. Okay. Slowly, subsequently, you will see what is that. So the spin number I can be determined from the atomic mass and from the atomic number. Okay, here you can see the half integer I, which things will have half integer I. If the atomic mass is odd and atomic number is odd, like your this hydrogen here, it is not visible clearly. In your material also it is there. So yeah, some molecules will have your half integer I, some will have, if half integer I odd atomic mass and atomic number can be, or atomic mass can be odd, atomic number can be even, but it will have integer value if atomic mass is even and atomic number is odd, and it will have zero value if it both are the having even number. Okay, so the spectra of several nuclei can be readily obtained since they have spin numbers I of half, and a uniform spherical charge distribution will be there. And most widely used NMR spectroscopy are C13 and proton NMRs. And the nuclei with spin number I of 1 or higher have a non-spherical charge distribution, and this assembly is described by the electrical quadrupole movement, which affects the relaxation time and consequently the line width of the signal and coupling neighboring things. Here, this coupling and the coupling constant, shielding due to the nearby environment, this everything will see with taking some examples. Okay, the spin quantum number I of the atomic nucleus varies according to the number of protons and neutrons in the nucleus. So, this point you must note down that spin quantum number I will depend on number of protons and neutrons in the nucleus. So accordingly, you can calculate. Okay. So in a nucleus, protons and neutrons have their own spin, and the spin number I of the nucleus is the sum of these spins. And the isotopes of an element have a different spin quantum number. Okay, and here you can see as you are increasing the field strength, your delta E will be increasing. This delta E, where you are having the delta E, your ground state is having alpha spin, that is plus half, and in the excited state it is having the spin beta spin, that is minus half. And the rules between the number of protons and the number of neutrons and the spin quantum number is here. So the mass number is what? P plus N, and atomic number is P. If it is even and this P is odd and N is odd, like 1, 2, then I will be what? I will be like 1, 2, 3, like this, and it becomes a integer. So such nuclei show a non-spherical charge distribution. Okay. Mass number, if it is even and atomic number is even, then in this type of nuclei, the transformations of the particles are combined, and that is they rotate in the opposite direction. And if mass number is odd, like your I, in that case I will be like half integer. Okay, half integer type, half or 3 by 2, 5 by 2. So this kind of things will show you in NMR spectroscopy. You can predict the NMR spectroscopic, you can use the NMR spectroscopic tool. So such course like C13 proton, then 15N, all these isotopic things. And since I is half, the NMR measurements of your proton NMR and C13 NMR atoms are performed. Okay. So this is the instrumentation. The if you recall the other spectroscopic tools where you had some source and it is just deliberating the radiation to pass through the sample. Here you are having this red tube-like structure is your sample holder. Okay, and the sample here in NMR, studying the NMR spectroscopy, is being kept in a magnetic field, is being kept in a magnetic field region. Okay, then you are having detector, then you will have some output device to scan the spectrum or to get the spectrum. Okay, and it is basically using your radio wave signals. So coming to this proton NMR spectroscopy, in order to observe an element in NMR spectroscopy, I should be greater than 0. Okay, it must not be 0, because in some cases you will find I will be 0. When there is no magnetic field, the magnetic moment is randomly oriented in all the directions. Like in figure A, you can see it is the random movement of these pins are happening. But when the proton or any nucleus, that is I greater than 0 when it is, and brought into magnetic field, their splits at different energy levels, and there is some uniformity you can see. So you can see here there is some uniformity in the spin movements, and it will split into two sections, different energy levels. If you see the equation, this delta E is h nu, you know from the Planck's equation in the first class itself we discussed, and delta E is also your this mu h0 by I. Okay, where this mu is your magnetic moment and h0 is the applied magnetic field strength, because you are here during the instrumentation you saw we are just using the magnetic fields, we are applying certain magnetic field also. So this delta E is equal to h nu, which is equal to mu h0 by I. So from here, the frequency can be calculated where your gyromagnetic constant is also present in the equation. H0, the applied magnetic field strength you are applying out externally, that is there, divided by 2 pi. So this frequency can be adjusted by keeping the H0 constant, and H0 can be adjusted by keeping the frequency constant. Depending on the study, which way you want to study the sample, you can tune these techniques. So coming to the concept of chemical shift and shielding, this NMR has a great utility because not all protons in a molecule have the resonance at the same frequency. Okay, so not all protons in a molecule have resonance in the same frequency. If you are taking a molecule, you are having 4 or 5 protons, you'll be thinking that okay, these 5 protons means they will resonate at a single at same frequency they will resonate. No, it's not that. Within that molecule itself, you have to see what is its position. Okay, accordingly we can predict. So we'll see through examples also. So this variability is due to the fact that the protons in a molecule are surrounded by electrons and exist in slightly different electronic environment from another. So got the point? Even if 6, 7 protons are there, uh, their electronic environment must be different or maybe different. Okay, so depending on the molecule to molecule, so the valence shell electron densities vary from one proton to another. The protons are shielded by the electrons that surround them. The protons are shielded by the electrons surrounding them. Shielding effect. Shield means like if you remember UV visible spectroscopy, while discussing that we discussed about inner filter effect. Means when your concentration you are increasing for the molecules, they themselves acts as the filter near the radiations. Okay, so here the shielding is getting done, shielding effect is getting done by the electrons that is surrounding to the protons. And in an applied magnetic field, the valence electrons of the protons are caused to circulate, and this circulate called a local diamagnetic current and generates a counter magnetic field which opposes the applied magnetic field. Okay, so here I will discuss clearly what is this chemical shift is and how it is varying shielding and de-shielding effects also we'll see. So in an atom, the local diamagnetic current generates a secondary induced magnetic field which has a direction opposite that of the applied magnetic field. As a result, your diamagnetic anisotropy, each proton in a molecule is shielded from the applied magnetic field to an extent that depends on the electron density surrounding it. And the greater the electron density around the nucleus, this diminishes the net applied magnetic field that the nucleus experiences. Okay, and as a result, the nucleus uh, precesses at a lower frequency, and each proton in a molecule is in a slightly different chemical environment and consequently has a slightly different amount of electronic shielding, which results in a slightly different resonance frequency. So, even if in a molecule you are having different protons, they will have different chemical environment and they will have the electronic shielding effect towards that protons may be different. So, eventually, what they will do? Eventually, they will have slightly different resonance frequencies. Here you see the concept of TMS, tetramethylsilane, will come into picture. We had seen various spectroscopic methods till now. Okay, might be if it is the unit 12, in every unit one spectroscopic method was there. Okay, everywhere you saw, I was talking about some reference, taking some standard solution, and calibration regarding the concept of calibration plots, how to use that calibration plots for determination quantitative analysis purpose as well as qualitative analysis purpose. Again and again, for different spectroscopic methods, we had discussed it. Here, for the NMR spectroscopy to be studied, NMR spectroscopy molecules to be studied through NMR spectroscopy. Here, the best reference is your TMS, tetramethyl silane. Okay, so the difference in resonance spectroscopy are very small, and it is very difficult to measure exact frequencies to that precision. Hence, no atom is made to measure the exact resonance frequency of any atom. Okay. Instead, a reference compound is placed in a solution of the substance to be measured. And here the reference solution is your TMS. And the resonance spectroscopy of each proton in the sample is measured relative to the resonance frequency of the protons of the reference substance. In other words, you can say that frequency difference is measured directly, and the standard reference substance that is used universally is your TMS. And this compound was chosen initially because what is the reason for choosing this material? The protons of its methyl groups are more shielded than those most other known compounds will be using. I'll show you the plot also where the DMS peak is coming. Okay, and at that time, no compounds which had better shielded hydrogens than TMS were known, and it was assumed that TMS would be a good reference substance since it would mark one end of the range. That range of chemical shift you will be seeing, okay, it is getting reflected at the one end. Here you just see this is the chemical shift scale, and TMS you will find the peak in one end of the uh, chemical shift or one end of the spectrum. Okay, before moving that, I want to tell you about this chemical shift. So, a field independent measure called the chemical shift is obtained, that is shift in hertz and spectrometer frequency in megahertz. The chemical shift is designated by delta. Okay, and this one for different molecules, this chemical shift positions changes due to its resonant frequency and with the excitation from the ground to excited state, and the shielding effect due to a nearby electron cloud also matters. Okay, and how if you are increasing the conjugation, what will happen, or if you are adding some groups, what will happen, that also we'll see. So most workers report the chemical shift in delta units or in ppm units of the main spectrophotometer frequency. Okay, and on this scale, the resonance of the protons in DMS comes exactly at 0 ppm. 0 ppm. That is why it is a best standard. If the standard is having the chemical shift value at 0 ppm, then accordingly you can say it is moving towards more shielding field or the de-shielding effect it is having, that it can predict clearly. So if you see NMR spectrum is a plot of your intensity. Y-axis you see it is intensity of the peak, and against its chemical shift that is reflected in ppm unit. Okay, in the x-axis, and TMS reference is at the zero position, and here you can see 0 to 10 is the your chemical shift scale. Okay, and if you are moving away from the reference peak, you say you are moving towards the downfield direction. If you are close to the TMS reference peak, you can say you are moving towards the off field direction. Okay, so increasing chemical shift is observed with increase in your frequency, resonance frequency. This range of chemical shift values for different type of protons. Protons, nearby proton varies this. I'm just doing this small way so that I can put a mark type. I hope it is visible. Okay. So here, what can be done? Here you see proton is attached to your nitrogen or attached to your oxygen or attached to your carbon, depending on which kind of different molecules you are using. It's like chemical shift, your off field, it is moving towards the off field direction or downfield direction. So these things you have little bit, you must have knowledge that if it is having aromatic hydrogen is there, Suppose you see 1, 2, third position. If you see third position, ARH is written, right? Aromatic hydrogen is there. So in which chemical shift, the region, in which region, what should be the chemical shift? Okay, near about 8 to 7 it must come. Like the way we discussed during the IR spectroscopy, if OH is there in a molecule, in which region its signal should come, in which frequency region the signal should come. That little bit idea you must have in order to do the structural elucidation. Otherwise it will be very difficult. Understanding this concept is having no meaning if you can't apply it in structural elucidation. Okay, for that you must know little bit thing. If aldehyde unit is there, then my chemical shift should come in which region. If acidic functional groups are there, then in which region I'm expecting. It may not be exactly same, maybe different environment also playing a role, but tentatively you can predict, okay, in this region I'm getting signal, means it may have the COH group. Okay, if I'm preparing a aldehyde but I am getting a peak at the acidic peak region, then from there itself you may get an intuition that okay, the thing I am going to prepare aldehyde compound, I have started with the aim that I will prepare aldehyde compound, but no, I am not getting that. Maybe during my reaction something has been gone wrong, that is why I am getting a acidic compound. So this information, when it will come to your mind, when you know what should be the region for the aldehyde unit is there, what should be the region for chemical shift, and if it is your acidic unit is there, what should be the region. Okay, so this is a rough, your this figure is showing a rough idea about the range of chemical shift values of different type of protons. Okay, so this rough idea you should have, like the way we discussed during your IR spectroscopy. So these chemical shift values of heteroatom protons, that is NHOS, SH, like that, in an NMR spectrum may vary with factors. There are various factors which will affect chemical shift. I was discussing just now. But you must have a sense towards the close proximity what should be the chemical shift. So H atom, H bonds, hydrogen bonds with other atoms, or use of different solvents, concentration of the assay sample, temperature of the spectrum. Okay, these things also can affect the chemical shift. And when D2O is added to the sample solution, they are replaced with deuterium and don't give a peak in the spectrum, because deuterium is a best solvent you can use. It will not give the peak in the spectrum. And here if you see this slide, the higher the electron density around the proton, the higher the H1 value and the lower the frequency of the proton signal. Means it will be showing you a shielding effect. Okay, it will be showing you a shielding effect. You can see this figure. In figure, this x-axis, this delta chemical shift in ppm it is mentioned, and just up to that you can see your frequency in hertz is there. But its frequency scale, you can see if it is higher frequency region, if it is moving, less shielding effect will happen, means you can say the proton is deshielded. And if it is moving towards close to 0 ppm or this side, then you can say it is moving towards low frequency, or it is more shielding effect you will see, and the proton is shielded. You can say proton is shielded. Here two points are there. So each proton gives peaks depending on the chemical environment. These parts we already discussed. Chemical environment is having a big role to study any kind of spectroscopy, not only NMR, any kind of spectroscopy. But if a question is coming, the factors affecting chemical shift, you must write in points that local diamagnetic effects that is getting generated by the electrons around the protons that also will affect, and the effect of magnetic fields generated by neighboring atomic groups that will also affect the chemical shift, because chemical shift in your NMR spectroscopy is having utmost importance. Accordingly, you will be getting the peaks and you can predict it is having which group in the molecule is having which groups, functional groups. Then magnetic anisotropy that we will see, and carbon hybridization, if it is changing, then also your chemical shift positions are different according to the hybridization, and electronegativity of the substituents, like the way we discussed during fluorescence spectroscopy, if you remember, then increasing the conjugation, your spectrum was shifting towards the longer wavelength region. So here also, if you are changing the electronegativity of the substituents, then your chemical shift also will affect. Okay. Then some of the electronic effects, nearby effects also matters a lot. Then paramagnetic shift that increases in proportion to the number of protons substituted with the halogens having higher electronegativity. These slides also I will share with you, because this is the only slide I have prepared. So magnetic anisotropy, what is that? So there are some types of your protons whose chemical shifts are not easily explained by simple considerations of electronegativity of the attached groups. For example, the protons of benzene and other aromatic systems have a chemical shift as large as that of the proton of chloroform. And the alkane, alkyne, and aldehydes also have protons whose resonance values are not in line with the expected magnitude of any electron withdrawing or hybridization effect. Expected value, you must know the expected value, but it may vary from that value depending on its environment and depending on its your anisotropic nature. And in each of these cases, the anomalous shift is due to the presence of an unsaturated system, one with the pi electrons in the vicinity of the proton in question. Means the proton which you want to observe the signal of a proton A. Suppose HA you want to study, so you have to see whether it is near to any unsaturated system, or whether it is near to any other functional group kind of system. So it also will get affected. The spectra also will get affected with that. So coming to the spin splitting, I'm having here 30 slides. Then again we'll be discussing the mass spectrum also. Then again we have to move to the structural elucidation part also. So today we have to finish the course. We are having many other things. Okay, just let me move with the spin splitting n plus 1 rule. Just let me take some water. Thank you. So, spin splitting n plus 1 rule. Here, just try to understand. These are the real application part, because subsequently you'll be seeing how to do the structural elucidation. The chemical shift and the integral peak area can give information about the number and the type of hydrogens that is contained in a molecule. So, number of protons available in a molecule as well as the type of protons available in a molecule you can predict from the this chemical shift values. Okay, and the other type of information you can found is NMR spectrum is that derived from spin splitting phenomenon. This spin splitting phenomenon will give you another part of information, as compared to your normal protons contain normal type of protons present in a molecule. Spin splitting also will give some additional informations. Even in small simple molecules, each type of proton rarely gives a single resonance peak. Okay, means simple molecules also you may not get a single resonance peak. You may get some additional peaks to it also. Okay, so in the NMR spectrum of this compound, you see here how many type of protons you are seeing. Two type. One is upper one is rounded and with the CH2 and nearby Cl is there and C is there. So both are having different environment, right? Though both are close to your carbon and chlorine, but the environment around them is quite different. So we can predict there will be two resonance peaks in an area ratio of 2 is to 1. In reality, the high resolution NMR spectrum of this compound has 5 peaks. Okay, a group of 3 peaks which is called triplet. 3 peaks means you can call it as triplet at your chemical shift region, that is 5.77 ppm, and a group of 2 peaks, that is doublet. Okay, here the coupling, the spin splitting effect concept is coming. If you are saying by seeing this molecule, I am having two type of protons, then I can predict two signals. Okay, I can predict two signals. But from where these triplet, three small peaks and two peaks are coming into picture? That is due to your spin coupling. Here you see the here this is the NMR spectrum of this compound. Here three peaks are coming. If you see towards the left of your spectrum, you are having three signals and here two signals, and towards the zero chemical shift you are having the reference signal of TMS. How to get that also we'll see. So what happened here, if you see the methyl CH resonance, that is 5.77 ppm, is said to be split into triplet, and the methylene resonance, that is coming around your 3.95 ppm, is split into doublet. Okay, and the area under three triplet peak is 1, and relative to the area of 2 under the two doublet peaks. The phenomenon is called spin splitting and can be explained empirically by the so-called n plus 1 rule. Each type of proton senses the number of equivalent proton n on the carbon atoms next to the one which is bonded to it. Here if you see, for the first figure if you see, this HA, okay, HA is near to how many how many other protons? HA is near to HB and HC. If you are following N plus 1 rule, then this HA is near to two more other protons, and so it is 2 plus 1 and it is coming as 3. So it will have this HA will have three peaks, like small peaks, but three peaks it will have. And this HP and HC, okay, they both will show a doublet peak, that is N plus 1, it is surrounding to your HA. Okay, so this is the thing. And here also you can see different molecules has been given here. The two equivalent neighbors give a quadrate, and two equivalent neighbors here gives your triplet, and here also one neighbor gives a doublet, and six equivalent neighbors will give you septet. So these things you can practice it at home, and if you go for the physical chemistry, Atkins or Banwell you can Banwell molecular spectroscopy you can follow, or other various books are there on based on spectroscopy, that also you can see. So coming to coupling constant, the splitting is okay, the splitting is there, but coupling constant concept is what? The distance between the peaks in a simple multiplet is called the coupling constant, that is J. And the coupling constant is a measure of how strongly a nucleus is affected by the spin states of its neighbor. Okay, and the spacing between the multiplet peaks is measured on the same scale as the chemical shift. Chemical shift is measured in different way. You can predict the shielding and desilting effect, and here the coupling constant is a measure of how strongly a nucleus is getting affected by the spin state of its neighbor, how the neighbor effect is playing a role. That information we can get from the coupling constant. However, chemical shift also in the similar way you can predict, but what functionality is there, what kind of nearby environment is there, that also you can predict through chemical shift. And the coupling constant is always expressed in Hertz. Okay, chemical shift you are expressing in terms of ppm. So here you just see the type of these things you must remember, the type of proton and the chemical shift region where you are expecting. The way I was telling you that here if acidic proton is there, then it will come around 10 to 12. If you are synthesizing a molecule and you are getting a NMR peak at 10 to 12, one peak you are getting, one or many some peaks you are getting, then you can think, okay, I may have this acidic group or aldehyde group, or your conjugation is there, or acetylene, or alkyne is there, alkene is there. So depending on the hybridization also your chemical shift values are changing a lot. So this raw information you must have with you, that where the signal is coming. Okay, so I'm just stopping here the NMR spectroscopy. Let us move to the mass spectroscopy. Then we'll see during the structural elucidation how we are using this chemical shift information, because during the structural elucidation we'll be using the concept of IR as well as this NMR spectroscopy also in today's class. So, just let me share with you the mass spectroscopy. Today is the last class and course is past. But I think we are always going in time because since 14 units were there, always I took care that at least I can cover 2 units in a day so that we can finish the course and we will have knowledge of everything. We touched everything. So, coming to this mass spectroscopy, spectrometry, you say measurement of that we discussed in the first class itself. So, this theory of mass spectrometry here, what happened? The molecule in the vapor phase is bombarded with a beam of high energy electrons. Just point to be noted here, the molecule in the vapor phase, okay, is bombarded with a beam of high energy electrons, bombarded with a beam of high energy electrons near about 70 electron volts. You can see 1 electron volt is your 1.6 into 10 power minus 19 joule. Then you can imagine how much energy you need to get a spectrum. Okay, so these electrons knocked off an electron from the molecule. This high energy electron beam, which is getting bombarded with the uh, your vapor phase of the system, vapor phase of the molecule, these electrons are knocking off an electron from the molecule, leading to formation of a positively charged molecular ion. Okay, positively charged molecular ion. This one you must remember, because while doing getting the spectrum, you will get a good signal for these molecular ions as well as its nearby this m plus 1. During that also you will be getting a good signal, or more appropriately a radical ion or radical cation. Okay, so this electron beam is knocking off an electron, so making the molecule to be a positively charged molecular ion, and more appropriately you can say it is making that to be radical ion. But this is one example has been given here. These radical ions so obtained have large amount of extra energy also. Radical ions are getting formed, but they also have a large amount of extra energy, which is much more than that required for breaking of the covalent bonds. Means the energy, that is the high energy electron beam that is getting bombarded with the molecule, is quite large enough. Okay, so after getting the molecular ion or radical ion also, it is associated with some extra energy, so therefore a highly energetic molecular ion undergo fragmentation. So subsequent fragmentation goes on, okay, yielding smaller fragments. So apart from getting the molecular ion peak, you will be getting other small peaks due to the fragments. Due to the fragments. That also you have to predict from the spectrum. Okay, and this as this molecular ion can fragment in number of ways depending on the nature of the molecule, the fragments provide clue to the structure of the molecules. From the fragment you can also predict something about the structure of the molecules. And the radical ion and the fragments obtained from the molecule are then separated according to their m by z value. Okay, where m is the mass and z is the charge of the ion. So this M by Z value is having very important role while discussing the mass spectrometry. Okay, and using your magnetic and or electrostatic fields, the record of M by Z value of this species against their relative amount or intensities is known as mass spectrum of the sample. This is a spectrum of methanol. Methanol is having molecular mass of your 32. So near 32 you are getting a peak. Okay, but at 31 also you are getting a peak, 29 also you are getting a peak, 15 also you are getting a peak. These things you are getting due to the fragmentation of this methanol molecular species. Okay, so, what is happening? This methanol, this molecular ion, it is getting formed CH2OH plus. It is having M by Z value at the 31. Here you can see at 31 point, means at 31 mass to charge ratio, you are getting a signal. So that is, this is the most intense peak and is called the base peak. Okay, it is called the base peak. We are also getting a small peak around 33. Here 32, a small peak is there also at 33. That is most probably the isotopic peak. The peak at M by Z 33 is a isotopic peak and called your M plus 1 uh, charge with plus. The main concept you need to remember that the molecular cation peak you will be getting, near to that you will be also getting a base peak. You will be also getting a base peak and small fragmentation peaks you will get. Also you will get some isotopic peaks. If you are assuming your molecule to be like this, then you might be calculating by yourself what is this its molecular mass. So I am expecting a signal at this position. If I am getting, then okay, fine, my molecule has prepared successfully. I have prepared it successfully. But if I am not getting the peak at that position, then there may be something else you are getting, some other fragments you are getting, and you are not getting a proper one. So that is why main importantly you have to see the base peak. Most importantly you have to say the base peak and the molecular ion peak. Rest other fragmentation peaks you can calculate, but after confirming that your molecular peak and the base peak. Okay, so here there was like how much relative evidence is there and where you are getting the peaks for the certain isotopic parts has been given here, and this is a spectrum showing the isotopic peaks. Okay, and coming to the instrumentation, there is one inlet device, then ionization chamber or ion source, you can say, then analyzer, then detector, and the processing unit or the output device. Okay. Here you are seeing one inlet chamber is there. Then completely this part, if you see, like the way we saw for the other, we discussed for the other spectroscopic method, here gaseous ion source is there where ionization is happening, then sorting of the ions through your mass analyzer, then your detection of ions is happening, then your signal processing unit is there, then you are getting the mass spectrum as an output. Then subsequently we are going to calculate what is its molecular mass of the compound for which you want to get the mass spectrum. Then you want to see what is its base peak line and molecular ion peak line. If both the things are coming fine, then you can do a subsequent your uh, fragmentation procedures. So inlet device, as you were discussing, this is this inletting or inserting the sample. This is a very very important step also. Here in this step, we avoid most of the contaminations and everything. And here in the mass spectrometry, the purpose of the inlet device is to load the sample into the ionization chamber. That is the same for all. The device used depend on the nature of the sample, because by seeing what type of what nature of the sample is, you have to use device accordingly. The solid samples are placed on the tip of the rod, that is called direct insertion probe, which is inserted into the evacuated chamber having the vacuum tight seal. But when you are dealing with a liquid sample, when you are dealing with a gaseous sample, the holding, the inlet device which is carrying the thing will be different. So this is the basic thing. And then you will have ionization chamber where ion source is there, or you can say ion source is there. And this choice of ionization method depend on the nature of the sample and the type of information required from the analysis. Okay, and here we are having gas phase sources also and disruption sources also. Ionization chamber, after ionization chamber you are having your mass analyzer, that is sorting of the ion, and then you will have detection of ions. Then subsequently you will have signal processing. Then analyzer, you are having magnetic sector analyzer and double focusing analyzers. Two type of analyzers are there. And detector or ion collector. Then you will have processing and output device, where you must notice the base peak, that is the important peak, base peak or your molecular ion peak. These two things you have to, first you have to see that things. Then coming to application of mass spectrometry, uh, even if it is mass spectroscopy or any other spectroscopy application, till now you have studied many many applications you have studied, like these all spectroscopic methods are having your biological applications, environmental applications, geological applications, and you can predict the adulteration part also. If some contamination is there, that also you can predict through your spectroscopic method. So this mass spectrometry finds an extensive application in diverse areas, like chemical analysis, of course, that is the major thing you can do. Structural elucidation means chemical analysis mostly is getting done in R&D sectors, in pharmaceutical industries. They are also very in a large scale mass spectrophotometry is getting used. Then in biochemistry line, then in clinical chemistry also it has been used. Then environmental pollution monitoring, food adulteration, then doping in sports and archaeology. So many sectors are there. Yesterday we discussed, wherever you are having, you are dealing with some elements, that is in soil, in water, everywhere you can use atomic spectroscopies. But it doesn't mean that, okay, all the atomic spectroscopies you can study for getting elemental analysis of this element, that element, every element you can get. No. As we discussed and we saw also, the detection limit varies from your spectroscopic method to method. Detection limit varies, as well as which kind of radiation is falling, that also depends. The source unit which you say, as well as the nature of the sample itself is important. Nature of the sample, how it should be, that is also important. Then only you can go for a particular study. You have to follow some literatures from research articles, and as well as sometimes it may happen that while studying theory is different while doing the experiment, you may face some problems where you have to tune the experiments and do trial and errors to get a result of suitability, or to get a proper result with a better sensitivity and with less background noise and background spectral interferences or chemical interferences. These concepts we already discussed in up to this many classes we have already discussed, so that all points you must remember throughout the spectroscopic method studies. Then here also you can determine, you can do the qualitative application, qualitative analysis can be done here. Mostly till now, if you observe that UV visible spectroscopy and atomic spectroscopic methods are most widely used for the quantitative analysis part. But however, when structural elucidation or qualitative application part is concerned, your IR spectroscopy, Raman and mass spectroscopy are quite helpful. Okay, these are quite helpful. So, the most common qualitative applications of mass spectrophotometry are this determination of molar mass of the analyte, because as I was telling you, every spectroscopy is having its special your specificity and its own selectivity. This mass spectrometry is capable of your determining the molecular mass of the analyte. However, your IR spectroscopy can tell more information about the functional groups present in the molecule. However, your NMR spectroscopy, if you think about, it can give you more information about how many protons are there, how many say carbons are there, or how many, what is its nearby environment. It will help in a way for the structural elucidation. So every spectroscopy is having its own beauty at its place. Okay. So the determination of it also helps in determining the molecular formula of the analyte, and determination of the structure of the analyte. Okay, and identification of the analyte also it helps to a large extent. Molecular mass of the analyte, how you will determine, because you will be getting a peak at the base peak you will be getting, or molecular ion peak you will be getting. Near to that you have to calculate which kind of which spectrum it may be. Okay, which sorry, you can predict what type of molecule it is. Like here you see the fragment lost list is there, and some peaks has been listed here. If, as I was telling you, as soon as you are seeing the mass spectrum, you have to see which is the intense peak. Okay, then you just see next intense peak is the molecular ion peak, and the intense peak is the base peak. From there, you got an information about your molecular species. Apart from that, you will be getting some other small peaks, which are due to your fragments that is getting created during the process of fragmentation. So these are some fragmentation peaks. You can also notice information, because few information, if it is in your mind, then it will help you while doing the structural elucidation. If you are preparing for the net get exams, then you can see the questions where structural elucidation has been done. See, we are showing you certain paths and we are telling you the information about the spectroscopic tools, how to use this, and what is to be done. But it's the you who has to practice it. You have to do lot of numerical solving, structural elucidation part, and numericals as well as questions. You have to try to attend that. If you are today you are listening to me, you are able to, okay, whatever madam is saying, okay, this is flowing in this way, you are understanding something. But when it comes to writing in pen and paper, and when it's coming to do an experiment by using this concept, when you will be getting, when you will be doing, once you are understanding the thing, okay, once you are understanding the thing, then only you can move on. Okay, fine then. So, identification of the analyte and single or in a mixture. Just a minute. Let me take some water. Okay. We are having one more unit also. But it's okay because once you understand the concepts, then you can move on with the structural elucidation. So, what we are discussing, that application part. So identification of the analyte you can do. Identification of analyte. This again and again we had used in other spectroscopic tools. Okay, how to identify a analyte, and there is quantitative application also in the mass spectrometry, but this quantitative aspect study are very less, and it has an important role to play in achieving this objective of uh, of the analytical chemist. Okay, it can be effectively used in the quantitative determination of the analyte alone or in a complex system with a large number of components, especially in the area of petroleum, pharmaceuticals, and environmental point of view. Okay, the heights of the unique peaks that you are going to get in the spectrum of different analytes in the mixture are indicative of their concentrations. Okay, the heights, the mass spectrum, you are going to get some height, and the height of the unique peaks in of different analytes in a mixture are indicative of their concentrations. Here this word indicative is having a great role while doing the spectroscopic analysis studies, because sometimes whatever generalization or whatever general theory we are studying for a particular spectroscopy, it may not be applicable when you are doing the experiments. But if something you are getting, some signal you are getting, it will be a indication to us. Okay, this may be the thing, that may be the thing. Okay, it gives us a indicative or indication about a certain things. Then we use our concept, use our literatures and various researches are going on. Then we come to one conclusion. Okay, so a calibration plot, calibration curve of the peak height as a function of the analyte concentration is quite useful in this kind of circumstances. How to use this calibration curve, that again and again we had observed in our other spectroscopic methods? We have to follow a standard whose signals are known to us. Okay, then only we can use that. Then okay, we came to summary. Okay, fine. So I am closing this thing, mass spectrophotometer. Then moving to the structural elucidation part, because structural elucidation is the last unit we'll finish today. Oh, I am happy. What?
Ma'am, myself Dipti.
Huh?
Uh, one question from Mass.
No, no. First, let me finish my units because only 30 minutes left. First, let me finish. Then, if time permits, we'll discuss. Okay? Otherwise, this unit only I will left for you. For you, I will not be able to finish my course. Okay. First, let me discuss this one. Then we'll move on. Then structural elucidation by various spectroscopic methods. Okay, this is the very important unit actually. If you see your organic questions in your net or gate or any exams where you are dealing with the organic molecules, you will be finding this kind of questions. And basically, the structural elucidation of organic molecules is getting done by using UV visible, IR, and proton NMR and mass spectrometry. C13 NMR also we use, and mass spectrometry also we use. We'll see one by one. For to start with the thing, what you have to do, compound is there. First, you have to calculate the index hydrogen deficiency. Index hydrogen deficiency. The index of hydrogen deficiency helps us to know about the number of multiple bonds. Okay, it is having triple bond or double bond or any rings present in a molecule. That information first will get from the indexed hydrogen deficiency. Okay, just a minute. So, how to do that? This is IHD, that is number of carbons present minus your number of hydrogen atoms divided by 2 minus the number of halogen atoms divided by 2 plus the number of nitrogen atoms by 2 plus 1. This is your IHD. If now we'll calculate for this molecule, whenever the question will come to you, it will come like this. A compound is there, its molecular formula is this. Just now tell us what is that compound is. Okay, so from the molecular formula, first you calculate IHD, number of carbon atoms. Here is 4, right? Then number of hydrogen atom by 2. Then number of halogen atom. Is there any halogen atom here? No. Is there any nitrogen atom here? No. Then plus 1. So it is coming to your 5. Okay. Then from where this minus 5 is coming? Can anyone say? From where this IST is coming? Minus 5. Okay, we'll see subsequently when it is maybe some mistake is there, or we can see various examples are there. From there also we'll get the point. Okay, so structural information you can get from the your mass spectrum. And here you see, as I was telling you, the molecular ion peak you must note down, and the base peak you must note down. Then some small your relative other peaks will be coming. that also you should predict. Okay, then this table I had already shown you in the previous mass spectrometry chapter. Then from the UV visible spectrum, you will get an information about your like into pi transition, pi star transition is there, or pi uh, bond is there, or n pi system is there, or from the shift in the delta lambda max value, you can say the conjugation effect, whether the molecule is conjugated or not. As I was telling you just 2 minutes before, that these are some indications that indications of, okay, my molecular species may have some conjugation or may not have some conjugation. This kind of indication information you can get from the UV visible spectrum. And IR spectrum, I was telling you, IR spectrum is very, very important, because the region of scanning, that is 3600 to 1200 centimeter inverse, is called your functional group region. Okay, that is the functional group region. While studying IR, I also discussed with you about the fingerprint region. Even if two molecular species are having identical feature or identical structural perspective, even then they will show you different indication or different signal in the fingerprint region. Like the way I was explaining you, two twins are there. If they are structurally similar also, but their fingerprints will not match. From there, you can get an information about the molecular species. So these regions you must remember some functional groups and where it is coming, like in this table it is mentioned. Okay, this table you see, this table you are having the information of, if I am having alcohol group, where I can expect the peak to be. Okay, if I am having alkane units, then in higher frequency region range, where I should get a peak. Okay, one by one we have to note down that. Then if aromatic ring is there, then where I am going to expect a peak. So basic things, at least carboxylic acid unit or aldehyde ketone units or benzene alcohol, these all little bit concepts you must have to predict your functional group regarding information. Because every question will not have all these informations. Okay, we'll also face one or two questions we'll also try to solve here. Okay, then proton NMR, this figure I was showing you. Okay, proton NMR. Similarly, you must note in mind that, okay, if I am having aldehyde unit, chemical shift, where it should be, chemical shift information also you should remember a little bit. Then only you can proceed further for the structural elucidation purpose. Now we'll see one example. Okay, a compound A is having molecular formula C3S6O, which shows the following spectra. Mass spectrum is given, and here IR spectrum is also given. Okay, and here NMR spectrum is given. If you see NMR, here around 2 to 3 one signal you are getting, and TMS peak you are getting at the 0, that is the reference peak. So here you are getting one peak only. So keep it in mind that one peak you are getting. And here in the mass spectrum, you are getting one signal at 58, another signal at 43. and many small signals and small due to small fragmentations and 1 at 15. Okay, and this IR spectrum around 1500 to 2000 you are getting a good intense peak, transmittance peak. Okay, and to also you are getting around 1500 to 1000. See, through this online class, I can show you one or two examples, but money you have to practice it at home. You have to practice it. Okay, and this one we'll see how to calculate this IHT. So number of carbon atoms minus your number of hydrogen atoms by 2. You remember the formula? C3H6O. C3H6O. Okay. So C3 number of carbon atoms. So it is 3. H6 here you are having hydrogen atom 6 by 2. Okay. Then halogen atom is not there and nitrogen atom is not there. Okay, so it is coming to be 3 minus 6 by 2. It is coming as 0. It means it is not having any unsaturation or ring structure. It is not having any unsaturation or ring structure. A strong absorption band in IR we observed at 1500 to 2000. If it is saying that exactly at the this 1700, if you remember your this region you have to remember little bit concepts, little bit functional group information you must remember. Okay, so around your 1700 you are getting a peak, strong absorption peak, so that is a indication that carbonyl group may be present. Maybe carbonyl group may be present, because you can't say oh acid will be present or this will be present, that will be present, because you have to see molecular formula also, how many O's are there, how many oxygens are there. Okay, then from the NMR spectrum provide two important informations. A single signal, we had seen a single signal, right, around chemical shift of around 2, around 2 we can see in our eye, that is around 2. If it is 2.2 exactly, that is different thing, but around 2 we got a signal, and that is a single signal. So a single signal indicates that only one type of proton is present in the molecule, and protons, all protons are the equivalent, because there is no splitting by nearby protons also. If you see this peak, this is a very clear NMR peak with a reference TMS peak and a intense peak at the just after 2. Okay, so here if you see, so all the protons are equivalent, even if it is there, because the chemical formula is showing 6 protons are there. Then a chemical shift of around 2.2 indicates that protons are highly deshielded. Protons are highly deshielded. If their shielding effect is you are getting, then it will be more with you will get a signal with more chemical shift value, and it may be due to being neighbored by your group, neighbored by carbonyl group. And from the mass spectrum you got prominent peaks at your 43, 58, and another peak you got at 15. If you are taking prominent peaks, that also is enough for you for the structural elucidation. The M plus ion appears to be at your 58. Okay, while the base peak is at 43. because base peak is the intense peak, right? Base peak is the intense peak and the molecular ion peak is less intense. However, it is having molecular mass of the compound. It is having close to your molecular ion peak, okay? Plus, it has already lost one electron. Then, okay, so you are going to get the M plus molecular ion peak at 58 and base peak at 43. And this M plus peak, that molecular ion peak, is in accordance with the molecular formula, and the base peak, another one, is an indicative of a stable COCH3 plus ion, because 15 you have to do the fragmentation like the way I was showing you in the mass spectrum. If base peak and molecular ion peak, you just concentrate over there, but you must do the fragmentation steps. After doing the fragmentation steps, you just calculate the m by z values and write in the side, write its m by z value. Somewhere you will be getting your m by z value to comes as 15 or whatever you require for your molecular species calculation purpose. So eventually what you are seeing, that you are going to get a compound like this, where again if you see this, now you can think of easily, okay, here three protons are there, here three protons are there, total six protons are there, and both are having like similar environment. That is why you are getting NMR a single peak due to a single high intense peak, and it is more decelerate, and that is because of the nearby CO group. And you are getting a IR peak, which is an indication of the carbonyl group, that also you are getting. Okay, so every information you are able to get out of this compound. So the structurally you can predict this one, but here I want to make you clear that you can't do the structural elucidation if you are not having the background little bit informations with you. If you are going to exam, you have to carry some little bit idea, like where my carboxyl group peaks would be, where my this, if alkane is there, alkyne is there, alkene is there, then where the peak information should be. Otherwise structural elucidation part is very difficult to do. Okay, so similarly, if you see another compound is given, then that peaks are there. Here you see 91 and 92 mass in mass. You are getting 91 one peak and 92 one peak. Then one is your 92 is your molecular ion peak and 91 is your base peak. Okay, and subsequently this 65, 51, 39 are the due to some other fragmentations, due to other fragments that are getting formed. But that fragmentation you must do of your own by taking pen and paper, that fragmentation this is coming are due to what fragment, possible fragments. Then here, if you see the spectrum of IR spectrum, where you are getting the intense peak, accordingly, you can say C7H8 is your alkyne or alkene or what to say, or alkane. You can predict that. Or if you think whether it is a aromatic ring type of structure, anything you can think of, because here oxygen is not there, nitrogen is not there, others, it is a very simple way you can predict. And here you are having but two peaks, here you are having two signals. Apart from the TMS peak, you are having two peaks, means you are getting one due to in the desilted region, one in the silted region. And this thing, whether due to some different chemical environment also possible here. Just let us see what kind of thing is there. Okay, this is the toluene one. Toluene one. This hydrogen which is there, okay, that will show you a different NMR signal, and this benzene ring, whatever your hydrogen is there, that will be showing you in another NMR signal. So similarly, when the question comes in your GetNet, you have to very carefully observe all the things, because only the molecular formula will be there, and later on you have to do the structural elucidation by the spectral informations that has been provided to you. Okay, not much information will be there. From mass, of course, from mass you will get some informations, but not that much you will be clear until and unless you are not remembering the frequency range, the wave number range of the functional group region that is in IR spectroscopy. That you must remember. Okay, that part is very important while doing the structural elucidation. Then NMR peak also will help you about the nearby spin splitting is there or not, or in how many type of signals you are getting. There, from there you can get information. So this material is very good enough to get to practice with various examples, and various type of examples also you can do it. Okay, so that with that we finished our 14 units, 14 units, and the spectroscopic method part also we finished. So now you can discuss with me, but today is my last class, and from maybe next class onwards, another teacher will discuss with you what are the spectral methods, sorry, not spectral methods, what are the separation methods. Separation methods, as I was telling you, this also you should put in your mind that just a minute, I am showing you this. In plus 2 you have already studied the this pH metry, conductivity metry, these all things you have already studied, so that will not be very difficult for you, but try to concentrate on your separation method unit, that you must concentrate on. See, in the first unit it was basic analytical chemistry, so you will have pH, metric, conductivity, basic concepts. Separation method is how consist of your different this chromatographic techniques, gas chromatography, liquid chromatography, various chromatographic techniques you will have. So little concentration is needed, and spectroscopic method as such you have already realized, you might have already realized how vast this portion is, and since you have not even studied during your plus 2 as well as BSc, so making me to make you understand, I have tried my best. And the electroanalytical and other methods, there you are having gravimetric techniques and other techniques. Okay, so these were our courses we finished with the electromagnetic radiation, UV visible, IR Raman, and which kind of molecules will show this kind of spectroscopies, that also we discussed. Then fluorimetry, phosphorimetry also we discussed, and fluorimetry even I showed you the instrument which I am having in my lab, that also I showed you. The cuvette and the sample holders and the sample keywords also I showed you. The application of fluorimetry, we discussed elaborately how you can apply the fluorescence spectroscopy. Also, I had shown you some literature, some research articles of mine where we have studied various fluorimetric techniques and fluorophores. Then atomic absorption, atomic spectroscopic methods, there were completely two blocks on atomic spectroscopic methods, that is flame photometry and flame atomic fluorescence, then atomic absorption, emission, difference and applications of AS, AES. We have extensively studied its quantitative applications and how this flame process can be avoided, and we can go for the electrothermal furnace method also we have looked into, as well as we had glimpse of discussion about the plasma source also, use of the plasma source also we had discussed. Then in the miscellaneous methods, NMR, mass, these are the miscellaneous methods coming into picture, because that will help you for the structural elucidation plan portion. But main thing is, apart from many informations you got through the classes, you have to read of your own. I will suggest you follow various nowadays you are having various websites with you for the your swayam courses is there, various MOOC massive online courses are there, that also you can see in order to understand these things also. Okay, so okay, just tell.
Hello.
Any so
Ma'am, can
today you are asking me the last question. Just summarize all the spectroscopies and ask a general thing. Summarize all my classes and ask a solid question.
ma'am, it's a simple question. Actually, I am humbled in determine in can we it is written somewhere that we can detect only positively charged fragment ions in the mass spectrometry. Uh, can we detect the negatively charged fragment ions there?
I don't think because see, the thing is, the electron beam radiation, what is the source over here? The source over here is electron beam high energy radiation. Okay, now you reduce your signal to noise ratio. Okay, fine. So, what is your source? Source is your high energy electron beam. When you are having high energy electron beam and it is taking out an electron, obviously you are going to get a positive charge species. There is no addition, there is no, you need to understand in a manner where energy you are giving to the system, and only this ionization is possible through taking off the electron. Okay, so basically you can go for the positive ion studies.
In case of if we ionize the molecules in fast atom bombardment method, then there will be no electron beam. We can only separate the positive and negative part of the molecule. Then where does this negative charge goes? Um,
There are you using your mass spectrometry method
yes, ma'am. The
or
if
other way of polarizing the negative and positive things?
I am, ma'am, I am telling about the fast atom bombardment method to ionize the,
Study
ma'am,
to
fast
ionize the sample. Okay, to ionize the sample, it's okay. But to study the mass spectrometry,
Madam, can we detect that negatively charged fragment of the molecule?
no, no.
Ma'am, what is the reason actually where why only positive?
Because it depends on the, as I was telling you, there is sensitivity and selectivity to everything, right? What someone is Nazrul IR spectrum, because there is selectivity and sensitivity to every aspects. This mass spectrometry is designed in such a way to characterize that part. Okay, IR spectrum. Nazrul, you want to say something about the IR
Yes, ma'am.
spectrum? I think you are talking about the oscillating dipole movement changes and all that things. But you can't, the mass spectrometry is having its own limitations too. Okay. Nazrul,
Okay, ma'am.
what you
Okay.
were asking about IR spectrum?
Okay, okay, ma'am.
Nothing. You wrote as such IR spectrum. Okay, fine. So I would like to wish all of you all the best. Do good somewhere from your graduation background, somewhere with PG background, for with the graduation background, and those are having a long gap in chemistry teaching studying. It might be a difficult subject for you, but I tried my best to simplify it in a way. And I have followed mostly the study materials which is available with you, so that it will be easy to get connected with. And I'll be sharing this slide with the RC Bhuvneshwar unit. You can take from there also. Okay. Uh, so with this, I think I will close the recording and close the class. Okay. So thank you all of you.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Thank you.
Thank you, ma'am.
Thank you,
Thank you,
ma'am.
ma'am.
Thank you.
Thank you, ma'am.
Yes, yes.
Thank you, ma'am.
Thank you all of you.